Good review. Location, electrons, I would say just outside. Officially, it's outside the nucleus. Protons,
Inside.
I'd say inside. This is where I would get more specific. Just call it nucleus. Neutrons, nucleus. Mass of the proton.
No, 1.
Proton was 1. Look at that. Me being a jerk and jumping around with the question. Mass of the electron now.
-1.
Mass of the electron would be 0. Okay. Charge on the electron. The charge on an electron is -1. Okay. Mass on the neutron. 1. Charge on the neutron. Charge on the proton. +1. Our symbols for, I think I heard electrons, so we'll go with that. E-, P+, and 0. What are our meanings? I would argue, and I'm not positive, but I think I've said it a couple times in that last lecture, on the meaning of a proton. So I would argue that's the easiest one to start with. What is the meaning of a proton? Okay, that's what it is, but what does it mean? Okay, if I say I have 1 proton, what does that mean? I have 1 proton. We need to take a step above that. That's what we're going for. Okay, we could start to evaluate a positively charged particle. That's still getting at what a proton is. I want to know what it means. If I have a proton,
You're the start of a nucleus?
it's a little bit more than that. I have a nucleus. I have a nucleus of what?
A single proton. No, proton and neutron.
It defines what the element is.
Defines the element.
There we go.
I have 1 proton. What do I have? I have a hydrogen nucleus. The number of protons will define your element. Okay. I can change the neutrons. I can change the electrons. That won't change the element. The element is dependent solely on the protons. Okay? Seeing a little bit puzzled looks up at the board. Is my writing of element confusing? Is that what that is? No, we're okay? Okay, just checking. This is why I say and write. You can hopefully match one to the other. So what do you want to look at now? Electrons or neutrons?
Neutron.
Neutrons. What do the neutrons mean? I would argue that they define the mass. Okay, we can get more sciencey, and I'll ask that sciencey question in a second here. Okay, neutrons contribute to mass. So if I change the number of neutrons, I will change the mass. But don't protons contribute to mass as well? Yes. So why am I not saying protons define the mass?
Because you already have a set amount of protons.
Once I've defined the element, I know the number of protons. I can't change the protons. How do I determine the mass of that element?
Adding the protons.
I have to add the neutrons into it. So the neutrons are really what's dictating that extra information. So the neutrons dictate that mass. Yes, I have to include the protons, but the neutrons are doing that last final step. Kind of make sense? Electrons. Nope, that's actually a little bit more relevant to a different word. The isotope is referencing different masses for the same element. What did we change to get a different isotope? The number of neutrons. So when we go back to our neutrons, we could say it defines the mass or it defines the isotope. Okay? So good call bringing in a nice sciencey term. Unfortunately, that ties to neutrons, not electrons. What else could we look at? What would the electrons contribute? No, the atomic numbers are protons. Okay? What are we getting in the back?
The charge.
The charge. Okay? Protons contribute that positive charge, but if I have helium, I know it has 2 protons. What determines the charge on that helium atom? How many electrons I've also added into it. Okay? If I add in 2 more electrons, I now know the charge on that helium atom to be Not negative 2. 0. Why would the charge be 0? There were 2 protons from the helium, or the proton. What word is that going for? 2 protons for helium, right, which is plus 2. If I add in 2 electrons, the electrons being negative will cancel out the protons. We'd end up with a 0 charge. So our electrons define our charge. Okay. We could bring in a sciencey word here if we so wanted. I'm not positive it's in the book yet. We could throw it out there and see what happens. Anybody got an idea? Let's give you a hint, actually. Let's play a little game here. 1, 2, 3 letters. Well, that takes all the fun out of it. Ion. All right, the number of electrons will define the ion. Okay, what charge state we're looking at. All right, that's all an ion is that it's a charged element.
Okay.
Okay? Make sense? Okay. Was that a nope or a yep?
Yep.
That was a yep? Okay,
Yep.
just checking. And then also to clarify, I just want to make sure, when we look at the periodic table, that was different than the nuclear notation, right? Okay. The nuclear or the atomic notation, as the textbook is referring to it, is useful for physicists, not so useful for us. Okay. Most people will organize, like on our periodic table, putting the atomic number above, because our periodic table is organized based off the atomic number. Okay, and then the mass down below, because we use the mass less frequently. Okay, it doesn't help us with the organization. Physicists really care about the mass because that determines if our nucleus is going to be exploding or not. Kind of make sense? Okay. So, quick question. How many people have downloaded the slides? What?
Just slide on campus.
Yeah. Oh, so nobody. So nobody is aware of what the next slide is. Oh, you mean like a quiz? That you're now put on the spot because you didn't prepare ahead of time by looking at the slides and you have no clue what's going on, and all of a sudden, bam, there's a quiz. So guess what? Bust out a piece of paper.
The structure of the pattern, he gives a basic. I can't find the word for it, but he gave us
One word to tie to Rutherford. Nucleus. That's all you got to tie to them. Right? Officially, you could add another word to it. Midas. King Midas. Gold. The gold foil experiment was Rutherford. Okay, that's how we got the nucleus. What'd you get in the back, Lauren? You're going to say Rutherford? What'd you have?
I put Mendeleev.
Mendeleev. Okay, that's a little bit harder. What was Mendeleev's contribution to atomic structure?
The rearrangement of the periodic table.
So Mendeleev organized the periodic table, not atomic structure. Okay, so valid scientist, an important scientist, but not answering the question that we're looking at. Bohr. What did Bohr give us? That might be a bit of a long shot because that's really coming solely out of the reading. We haven't even gotten to Bohr yet.
It talks about the electrons and like the jumping of electrons.
Showing where electrons can exist.
They're,
Okay. And we'll talk about orbitals and levels and all that fun stuff too. But Bohr contributes to our atomic understanding by looking at electrons. Other scientists. Curie. What did Curie give us? The discovery of radium. Does that have to do with protons, neutrons, and electrons? Laid the way for it because with that purification of radium, what can happen?
they were able to shoot.
We can now create an alpha particle gun, effectively, that we can use to aim at gold foil that Rutherford did to give us a nucleus. All these little jumps around. Kind of make sense? Provide a topic to be discussed. Oh.
Orbitals.
Okay, orbitals. How would we know what the topic was to be discussed in this point
Based on
forward?
our reading, and that's what we got
In
out of it.
theory, it should be based off the reading, okay? Because I talk too much about slower things, you end up reading a little bit further ahead than I lecture on, but in theory we should be getting to that. Okay. How would we know that? Yeah, there we go. We downloaded the slides, and then we had the slides. We go, oh, Mike can really only make it through about 10 slides at a time. We're going to talk about those 10 slides. Okay. Ideally, I go faster than that. That's what we got. Isotope was isolated with 88 protons, 138 neutrons. Atomic notation for this element. Okay. We talked about it. Your textbook calls it atomic notation, and I call it nuclear notation. Okay. So how do we use that notation? Okay. Our notation was we had a symbol in the upper left-hand corner. What are we putting?
That's the weight or the mass.
Officially the mass number, which is equal to protons plus neutrons. And then in the lower left-hand corner we have the atomic number, which, yes, is equal to the number of protons. So when we go through and do this, we can start this off and say 88. Now what? Okay. And actually, we even heard an argument that, well, we know the protons plus the neutrons. What'd you say the number was?
It was 226.
226.
And then you can say the symbol.
The symbol is tied to our atomic number, and we have Ra, also known as radium. Why would Mike pick this one? Radium gives us the gold foil experiment, the existence of a nucleus. Cool. Kind of make sense? Okay. We're good with that.
Lesson learned. Go over the slide.
Okay. Lesson learned. Let's go through the slides. Isotopes. All right, let's address our isotopes because this is based off of our neutrons first. For those of you that wrote down, that is exactly what I wanted you to do, but I also don't want that sheet of paper. You can keep that. That's my gift from you to me and back to you without even coming through me. Okay. Our protons define the element. The neutrons define the isotope or the mass of that element. Right? So when we think of hydrogen, okay, we get the symbol, atomic number 1, which gives us the symbol H, and the mass number is 1. How do we know the mass number for hydrogen is 1? How do we know it only has 1 proton? I like where you're looking. Where are you looking?
Periodic table.
Periodic table. Where are you looking on the periodic table?
Looking at the atomic number, the weight, you look at the atomic weight.
The atomic weight, which is the number underneath,
1.
okay, and it says 1, which means more than likely
There's only 1 proton in
there's only 1 proton, and how many neutrons?
it. 0.
0. So that would be our symbol. Okay, 1, 1H. So far, so good? Okay. It turns out that we can change the number of neutrons. Okay, that's why it determines the mass, or neutrons determine the mass. And if we look at hydrogen, okay, we have another form of it. We could add a single neutron to the hydrogen nucleus, and by we add, existence adds, we find okay, that some hydrogen has a neutron. Well, that means the atomic number will not change. It should stay 1. But the mass number should become
3. No, the 1 gets canceled out.
there's 1 proton, and we added
1 neutron.
1 neutron. What is the mass of 1 proton? 1. What is the mass of 1 neutron?
1 to 2.
What is 1 plus 1? 2. And we have 2. Right? Okay. These hydrogen atoms have different masses, which means they have different physical properties. Okay? We're all humans, at least very good replicas of humans, if you weren't a human already, okay, in this room. We could go through and say we were all the same human, okay? But we have different properties. We have different masses. Because of that, we don't just say, hey, human, human. Answer the question, human. Okay? We come up with names so that we can classify and better understand those things. Okay? So hydrogen, being the simplest element, gets studied a lot, and we've looked at the different isotopes. Okay? Because I now want to be extra clear when I'm looking at hydrogen with a mass of 1 versus hydrogen with a mass of 2, I provide a new name for it. The names for those, protium and deuterium. Why protium? prot sounds an awful lot like
Prototype?
proton. And if we think about the hydrogen nucleus, what is in the hydrogen nucleus? Only a proton. So why do we call it protium? Because in the sample of protium, there is only one proton. That's why we call it protium. What happens when we move to deuterium? Well, it's a proton and a neutron, so I can call it protineutrium. That was a bit goofy. So we come up with a different name. They call it deuterium. Why deuterium?
Because well, do sounds like two in French.
Duet, deuce, okay, deuces are all in reference to two. Right? Because the mass of a deuterium is 2. That's why we're looking at deuterium. Okay? Yes.
So if we're breaking down this word for meaning, what part of the linguistic aspect of writing is that?
Oh shit.
Starts with an M.
Habit.
Morphology.
Morphology, there you go, the smallest part of the word.
Sorry.
Just because some people have heard of it, and it almost always shows up in movies and sci-fi movies as this big amazing thing, so let's just kind of address it. You might have heard of the magical mystical property of tritium. Dun dun dun, magic thing.
Doc Awkward is trying to make it the same.
Try for 3.
Now, does this go across the periodic table completely? Like, if you see a tribe ahead of like other things, it's most likely going to be their whole.
They're referring to 3. The question is, what is that 3 that they're referencing? Yes, until we classify what that 3 is, we don't know. In this case, tritium is referring to a hydrogen atom that has one proton. Why is there one proton? Because it's hydrogen. How did I get 3? 2 neutrons. And we have tritium. Guess what? Also exists. Okay, we can find it. Right? In nature. Just exists in wherever you have hydrogen, you will encounter tritium. Okay. Which is kind of getting to our next kind of question behind this. When we talked about the periodic table, we had the atomic number, which was consistent with our nuclear trend, or our atomic notation. And then we also had the atomic weight, which we said was not the mass number. Similar to, but not the same thing. What did we say the atomic weight was derived from? Did we say that? Where did we get that number from?
The weight?
Weight of what?
The element? Is that what
Yeah,
you're saying?
it's the weight of the element. Okay? But if I take a look at hydrogen, I've got 3 hydrogen elements with 3 different masses. Okay? So the weight reported on the periodic table is going to be the average mass of all of the different isotopes that I could find. Make sense? So that's why when we look at the periodic table and you look at the numbers, those weights, how many of them are whole numbers? Very few of them. In fact, the only ones that are whole numbers are the man-made ones, because we made probably 1 of them.
What about the 52.00?
52.00. This gets into sig figs, which works for you, okay, because you had the lab on Tuesday. Okay, we haven't talked about sig figs yet in the lecture that gets pushed into the next unit. Okay, but what's happening is when we include that 00, we're adding some significant digit information. That it is not exactly 52. It is 52.00. Right? I don't know what the next decimal place is. If I wanted to, could I find a balance that would measure it? Yes. Okay. Why do I not report more decimals?
That's insignificant.
Kind of gets to insignificant. Do I really want to carry 20 decimals through every calculation? No. Okay. Because if we could also bring in the aesthetics of it, it would look awful on the periodic table if we had 20 decimal places after each of those numbers. Okay? And I don't think we know them all that precisely. Okay? But we can get a lot more accuracy out of those if we wanted. Okay? Which brings us back to the example we've got here. So what we said is what we're reporting up there on our periodic table is the average mass for our atoms. Okay, well, what was the mass for protium? Protium. 1. What was the mass for deuterium?
2.
The mass for tritium? 3. If I want the average, what do I now need to divide by?
3.
3. What would I get as an answer? Not 1 is a good answer, but we can do a little bit better than that.
You get 2.
We'd get 2. So the average mass for hydrogen, according to our calculation, is 2. And we look at the periodic table, and it says
1.
not 2. What information are we missing? How many of each of those individual isotopes are present in any given sample? And it turns out that if we took a sample of 100, it's probably not even going to work with 100, 99 of those hydrogen atoms would be protium. 1 of them would be deuterium. Even that's, I think, technically wrong. 99.99% of all hydrogen in the universe, we can't go quite that far, within our testable realm, is protium. What is the other 0.01%? Deuterium. Well, that covers all of it. Where did tritium come from? Deuterium is 0.009. What is tritium? 0.0001%. Okay? So the amount of tritium available to us is insanely small. We do not have a lot of tritium accessible to us. The amount of deuterium is really, really, really small. Most of hydrogen comes in at protium. Okay? If we look at the average, what would we expect to see on our periodic table then? If most of it has a mass of 1, I would expect the mass to be reported on the periodic table really close to the number 1. Would I expect it to be higher than 1 or lower than 1? Okay, why are you saying not lower?
Because by definition, it has to have at least 1 proton. So
Okay.
it's gonna have it in conflict.
So there's a fair answer. We're saying it has to have at least 1 proton, so there's no way it can be less than. So we've reached kind of a limit there. But let's say we picked, say, I want nitrogen. Okay. Nitrogen, actually I can't do nitrogen because I don't have that one memorized. Carbon. Carbon, we have carbon 12 and carbon 13. Okay. Which one do you think is more abundant? Why is carbon 12 more abundant than carbon 13? What was that? When we look at the periodic table, the average mass, that's what's reported on the periodic table, is not just 12, 12.01. That number is closer to what? 12 or 13? 12. Okay, because it's closer to 12, we would expect carbon 12 to be the higher in abundance. Okay. Would I expect that number to be under 12? Notice it says 12.01. Couldn't it have been 11.99 and still been closer to 12? Yes. Why is it 12.01 and not 11.99?
Because once you drop below, it's no longer carbon.
Nope. Dropping below doesn't matter because I can change the number of neutrons. It can still be carbon with the same number of protons. Why would I expect it to be 12.01 and not 11.99?
The average of all of the isotopes?
It's the average of all of the isotopes. So if it was just carbon 12, the average comes out at 12. I'm telling you it's not just carbon 12. I'm telling you it's carbon 12 and carbon 13, which means the average will have to be higher than 12 so that I can account for the higher mass of carbon 13. Kinda, sorta?
Yeah.
Okay. There's a fun little exam question that shows up on that. Okay. So if you're curious about that and wondering, I'm not quite sure I would see that as an exam question, look at the practice exam. You'll see it. Okay. How many protons and neutrons does an atom of lead 206 have? And then I started thinking about processing how we do it. How do we organize what we do? Okay, and how we should think about questions. Like, actually, this is a pretty genius question. I should ask this a lot. Okay. Protons and neutrons. Okay, so I heard a couple people saying, well, protons are tied to what? Okay? Our atomic number. Okay? The neutrons tied to,
Atomic weight.
so just the number of neutrons is the atomic weight?
No.
No.
Isotope, though.
Okay. If I take the protons and the neutrons, now we could potentially get the atomic weight. It's not actually the atomic weight. It needs to be the, sorry, that was supposed to be an M, and instead it became an N. The mass number. Similar to the atomic weight, but not the same. The atomic weight is the average of all isotopes. Is this saying the average of all isotopes of lead? No, it's saying very specifically lead 206. Have we seen that format, lead 206, written before, in the class at least? You may have seen it in your textbook. I'm just saying in the class. No. Okay, so Mike's a jerk. He's formatted a question that he hasn't taught us. But have I taught you enough material that you can reason your way throughout to figure this out? Yes. Okay. That may not be inherently obvious, but it is there. Okay. The next part of this would be trying to figure out what we have, because the atomic number, I got lower left-hand corner. That's great if I gave you the atomic notation. Do we have the atomic notation? No. What do I give you? I give you this word, lead 206, and I give you something else. In fact, there's nothing else written up there, Mike. Well, I gave you all that stuff about deuterium, protium, and all that. Anybody look at that information? No, why not? It's useless. You can ignore lots of stuff when you read a question. Focus in on the important stuff. Give you lead 206, but I am giving you something else. What is that something else I have given you? I did not tell you the protons. I did not tell you the neutrons.
It gives one atom.
Yeah, I can accept that. I did give you one atom. Does that help you?
Yeah. I mean, in the end, the average.
Well, we aren't doing an average, so it does simplify the question. But even if you know it's one atom, that doesn't tell you the mass number. That doesn't tell you the atomic number.
If you know the symbol for that, you don't know.
Okay, if I know the symbol for lead, how does that help on this question?
You can find out on the periodic table.
What's the other thing that I gave you that you are implying? You have the periodic table. Okay? And you would better be able to read it. Okay? And what you were suggesting for the first part of the reading it is recognizing that the periodic table gives us the symbol, and I need to know that lead as a symbol is PB. Once I know that information, I can now hunt on the periodic table until I find PB. And what do I find when I look at PB?
Its weight is 207.
Okay, we get two things that we get out of this. I keep finding it and losing it. I got 82, PB, 207.2.
Sounds reassuring about the chemistry teacher losing the element on the table.
Okay. PB I know is now lead. What is the 82?
The protons.
Let's take a step back from the number of protons, yes, but first, it's the atomic number. How do I know that's the atomic number? It says so on the periodic table. I'm not in the atomic notation. I can't say lower left anymore. That's false. Okay? I'm on the periodic table. It's a different format. So I know that 82 is my atomic number, which means what? We know the number of protons to be 82. Cool. To figure out the number of neutrons, what do I need? I need to subtract the 82 from the mass number. What's the mass number? 207 is not the mass number. Read our table. Does it say mass number? No. What does it say it is? It's the atomic weight. 207, false piece of information. Crap, I don't have the mass number. Right? Multiple choice, I can process of elimination through. I know the number of protons has to be 82. Okay? Guaranteed on a multiple choice test, one of your answers says the number of protons is 206. Okay? We know 206 is wrong. It has to be 82. So eliminate some answers. Okay, to figure out the number of neutrons, what must I know? The mass number. I have to know that. Well, the periodic table didn't give it to me, so what does that mean? The question had better have given it to me. Is there a number floating around in there? Our 206, this is a different notation for how we can reference the isotope of an element. We can give the element name followed by the mass number.
So what is the difference between mass number and atomic number? The atomic weight?
The atomic weight is the average of all isotopes. The mass number is the mass for an individual isotope. And yes, it is an irritating nuance, but it is a valid nuance nonetheless. So we can take 206 minus 82, and I'm guessing you had 124 in the back. Is that where your 24 came from? And 124 is our number of neutrons. Okay. There is no way I will be able to give you all of the content. That can't happen. What I'm trying to provide you with is enough of the content that even if something spins out slightly out of that realm, you can think and reason your way through it using your abilities to think and reason through questions. Make sense? 1, 2.
Does lead 206 even exist?
Yes, lead 206 does exist.
Okay.
What's your butt? No. Go ahead. Push it.
We just got finished
Yeah.
saying that it can't be less than the original average.
I said if we had carbon 12 and carbon 13, the average of those has to be somewhere in between. Lead 206. If I say lead 206 exists, what can you tell me?
But there has to be something higher.
There has to be another isotope that has a higher mass. Why?
The average is just.
Because it averages out at something higher than 206.
And it's got to be higher than 207.2.
And it has to be higher than 207. So I could have lead 208 or lead 209. By looking at the scale of those numbers and understanding something about kind of how we average things, we can come up with that predictive ability. Yes?
So is this how like the solved problems are going to be working? You want us to just like not just a little, even if we did have the answer at the top of our head, we did it like mentally?
Yep.
You want us to just...
So this would be a good question for a solve. Okay, your solve homework. Sorry, different class. When you see the solve homework show up in your assignments, okay, and you saw this as one of the questions, all that's written there is what I would expect you to write as your work. Okay? I don't need the question, but saying protons is atomic number. Neutrons is the mass number. Okay? Neutrons plus protons is the mass number. Okay? Showing all of that extra written in work, that's what I would like you to do. Okay? The next part of it, what if you were supposed to write out an explanation on how you solved? Okay? Well, you could write out, I looked up, or I knew the definition of atomic number to be the number of protons. Okay? I knew the definition of neutrons. Neutrons plus protons is the mass number. I didn't know this format of lead 206, but based on the information given, 206 must be the mass number. That means my neutrons is this. Make sense?
You gave us the mass number in a question.
206 was the mass number.
That answers the entire question.
No,
You said how
it
many
helps. I'm asking for, that's now getting the linguistic aspect, okay, which chemists are notoriously bad at, believe it or not. This is asking for protons and neutrons as a separation of each other, not as the sum total of them. The difference in the question would
So
be...
you might be able to say, well,
I don't know how to format that.
I was list
Linguistically.
both protons and.
There you go.
But, yeah, we could find another way to say it.
We'd have to, and if it comes down to it on an exam where it's show your work, okay, you can raise your hand and be like, do you just want the sum of those two? Is that what you're asking for? And I'll be like, no, I'm not. I'll write it up on the board and announce, no, I want to know the protons, the number of protons, and I want to know the number of neutrons, and I'll clarify that. There you go. Hey, look at that. How did I figure that out? I talked it. I said it out loud, and it worked, right? So this is why we should read our essays. Out loud. We good?
Yes, sir.
Okay.
I have a question.
Now that I deleted everything, go ahead.
Although, like, just to clarify, an isotope can be like of any weight or mass.
Any element has the potential to have an isotope, yes.
As long as it's over the weight of the protons, right?
What is an isotope?
It's when
Or if we go back to, come on, here, which of our subatomic particles told us information about?
neutron.
Yes. So to get the isotope, all we're doing is changing the number of neutrons.
So, like, as long as the weight, or no?
Your mass will always be larger than the number of protons because you had to add neutrons. So the mass will always go up from the number of protons.
So it could just be one neutron and that would be an isotope.
Yep.
Okay, just one. Sorry.
Yep.
Except for hydrogen, then about the same.
Hydrogen could have a neutron. It could have two neutrons. That's why we had protium, deuterium, and tritium. Okay. This gets us into kind of the mathematics side of it, which I try to hold off on as long as possible, but I get broken every so often and we have to bring it in. Percents are unitless ways of presenting information, okay, which goes all the way back to our chapter 2. Okay? We're looking at expressing the amount as a total, out of a total possible. What is that total possible when I think of percent? 100, because cent is 100. Okay? Centurion, century. Those are all looking at roots of 100. So when we're looking at a percent, we're saying some amount per 100 of that sample. Okay? Depending on the size of our sample, we want a way to kind of arbitrarily adjust and scale. I don't have to measure 100 of my total sample. I can measure any amount of my total sample, and as long as I multiply by 100%, I set myself into that percent system. It is unitless. That means the units I use for my one quantity up top must be the same units that I use for my sample. So if I'm using mass, it's got to be divided by mass. If I'm using volume, it's got to be divided by volume. This is why when we look at percents, you will often sometimes see, or should always see, an extra little term, percent by mass. That means when I ran that calculation to determine what that percent was, I determined the mass of the things that I'm looking at. Right? You will notice that it is rarely included in our textbook. Right? And this isn't because chemists and ultimately scientists are inherently lazy, and we end up implying that information. Okay? If I'm going to look at the percent gold in a necklace, okay, am I going to looking at a percent by mass or a percent by volume? What phase is gold? Solid. What's the easiest way to determine the amount of a solid? By weighing it, I get the mass. So it becomes implied into the phase system. If I want to determine the percent of alcohol in my drink, I'm typically going to report that as a percent by volume because alcohol is a liquid, water's a liquid. So we're looking at a percent by volume.
Right,
Okay.
because volume is for things that really don't, they fill.
And volume is really only used to measure our liquid phases, okay, or potentially gases. Okay? So it is sometimes implied. It shouldn't be. It should be explicit every time you look at it. Okay? So let's take a look at an example. Bronze is an alloy of copper and tin. If a sample of bronze contains 79.2 grams of copper and 10.8 grams of tin, what is the percent copper in the bronze? Okay, there's a second question there. I'll make you do that. Let's walk through the first one, though. Okay, what am I looking for? The percent copper in bronze. So to solve, my percent of copper is going to be equal to the one quantity. What quantity am I going to be looking for? Copper, because That's what I'm looking for.
That's what you want.
Okay? So I want the copper up top. What do I want below?
Wait, total sample,
I want the total sample. The total sample is known as
bronze.
bronze. I almost always forget it with percents, but then you got to multiply by 100%. Do I want to be doing this as a percent by mass or a percent by volume?
Mass.
Why mass?
Solid objects that you're weighing.
They're all solid objects, and it was given to us in a mass unit in grams. Okay, so what was the mass of copper?
79.2 grams.
79.2 grams. What was the mass of the bronze?
90.
Okay. This is where we can run into issues with showing work. I have no idea where you pulled 90 from. And I know that you're like, that's a simple calculation, Mike. You can't be that stupid. I can't see that. You got to show me.
Bronze equals copper plus tin.
Bronze was copper plus the tin. I already forgot the tin number, 10.8. That's an 8.
Is it in there?
Okay. I will very often see students do something along these lines. I already accounted for the 79.2, so I wrote that up there, so I don't have to write it again. How much copper is in 10.8 grams of tin? 0. There isn't any. That's why we called it tin. Okay? So be careful in your analysis that what you're including includes all of the information necessary. You may have to repeat your numbers. Okay? This would then give us 79.2, and as a couple people pointed out, equals 90, or our addition is 90. And if I do that math really quickly, I believe we come to a number, drop, carry, oh, forgot to multiply by 100. We multiply by that 100, we get 88.0%. And we now know the percent copper and bronze. Questions? Aren't I really good at math? I just did that all in my head.
I was going to ask if you did. If you had like a calculator on your iPad right there.
Keep it up for
Or you've done this problem a lot.
We'll see in a second. I got a pseudo magic trick. Questions about that format? Okay, you're going to do the next part. The second question, how much tin is in 100 grams of bronze? For those of you interested in that magic trick, check out the lower right-hand corner. I forgot. I actually had solved this one already. So the other class is a little bit further ahead so far. When we went through and did it, we solved it a slightly different way. But a suggestion came in back. We want 100 grams for the sample. That's the total sample, was 100 grams of bronze. Okay, so I can put the 100 grams on the bottom. Then there was a suggestion, well, I want to put 10.8 grams of tin up top. Okay, there's a couple issues with that. That 10.8 grams belongs in what size sample? A 90-gram sample, not a 100-gram sample. So that doesn't work. Okay, so it could just be an unknown. I don't know what it is. Okay, if it was 10.8, then that's the answer. I'm done. There weren't any calculations. Okay, so it's unknown. Multiply by the 100%, and then this would then have to equal what?
Can you repeat that?
Would have to equal what?
Before that?
Our percent of tin in bronze.
Oh, has to equal the percentage of tin in the previous.
Yep. Do I know the percent of tin in that sample?
Yes.
Okay, you can find it.
I can find it. How could I find it?
You know, 88% of is copper, so you can 88, and you know it's 100% total.
I know 88% of my sample is copper. Okay. There's some X amount of tin percent, and if I add those two numbers together, what do they have to equal? 100% of the alloy, which means I now know tin is 12%.
Can you just show that?
How much of a work, again, do you need to show? You should be showing as much work as possible when you go through and solve. Okay? And you might say, well, what happens? How do I get the 100 to the other side? Rhymes with divide.
When we do like time tests,
Yeah, everything is timed. You only get the class period.
Would you, when we do type this, you still want us to?
Oh yeah, you need to show all that work. Yep, you will have time.
So Mike, would you say a good rule when approaching the solves and trying to determine how much work to do does go back to that peanut butter jelly tie, that exercise we talked about?
It's a good idea.
Someone, if you, in the same way, you want someone to be able to duplicate the process you went through, and that's how much work you show. In the same way that if you are trying to tell someone to make a peanut butter jelly sandwich and forget a step, they might end up using their fingers to spread the peanut butter on the bread.
Does that make sense? Everybody hear that? And yeah, it may be a bit brutal for some of this stuff because you're like, dude, I can divide by 100 and multiply by 100 and then I get 12. Okay? Yeah, that's true. You can. I need to be able to understand that you understand that. There's that whole reverse back and forth for me to be able to grade. That's also why I probably wouldn't ask this question and show your work, because the amount of work for you to show, a lot of people could skip those steps. So I end up leaving those out. Kind of make sense? Okay. So let's actually move back to our sample for hydrogen. We're going to look at our mathematical system. Remember when we looked at hydrogen? We said we had hydrogen 2, we had hydrogen 1, and we had hydrogen 3. Okay, so that was protium, deuterium, and tritium. And if we were going to determine the average mass, we take the mass of hydrogen 1 plus the mass of hydrogen 2 plus the mass of hydrogen 3, and we divide it by the total number, which was 3, and we would get 2. And that didn't make any sense because it's not what's on the periodic table. Okay? What we're looking at here is a weighted average. Okay? In this calculation, you've made the assumption that all of those have an equal percentage in the system. So what? But I didn't do that in the calculation. Yeah, actually you did. Okay? Believe it or not, it is buried in there. Okay? So we're going to do a little bit of mathematics to pull that out. It's the same as taking 1 over 3 plus 2 over 3 plus 3 over 3. Right? Everybody okay with that? Okay. This is the same as saying 1 over 3 times the mass of protium, which was protium, prot 1, plus 1 over 3 times the mass of deuterium plus 1 over 3 times the mass of tritium. What are those 1 over 3s?
The percentage of
The percent of each isotope. So in our calculation of determining the average, we factored in and said that the percent of protium was 33%. The percent abundance of deuterium was 33%. The percent abundance of tritium was 33%. We said they were all equivalently weighted. And if they're all equivalently weighted, we get 2, which is not what's reported on the periodic table. Okay? So what we've done is kind of broken down the average calculation so that we can see the component pieces. When we go through and take an average, we can imply that they all have the same weight, or we can say that they are weighted. So if we look at a weighted average, we'll take the percent of the first species times that property of that species, plus the percent of the second species times that property of that second species, plus percent of the third species times its property. And we'll do this until we've added up all the species in our average. Okay? That looks an awful lot like a formula for how to solve weighted averages. Kind of because it is. Okay? We can use that formula if you want to memorize it as a formula, or you can remember how to break down your averages on where they're coming from. I personally suck at memorizing formulas, but I can take stuff apart. I will take stuff apart every single time, which, as Braxton was asking about, that means you'd have to spend more time showing work. Okay? When I spend the time showing the work, I get the question right. If I attempt to memorize it, I don't memorize it, and I get the question wrong. I have favored getting the answer right over getting the answer wrong fast. Okay? That is your call. If you would prefer to get the answer fast but wrong, by all means, go ahead and do that. I will recommend that you don't, because that is an awful way to pass a class. And I would recommend that you slow down, show your work, and get the answer right every single time. Make sense? So, shall we apply it? What's the question before I delete
I
everything?
have a question about your grading.
What about my grading? It's always right. No, it's not.
If we show all working and we get the answer wrong, like, do we get points for working?
Let's do that with the next one. Let's see if we can do that with the next one. Did I cheat and give myself an answer? Oh, man. Really? Yeah. Oh, man, really. That sucks. Oh, well. So let's take a look at this. Gallium has 2 isotopes. Because I don't have the answer, I will need some calculator help from you guys. Gallium has 2 isotopes. Gallium-69 with a mass of 68.926 AMUs. What is an AMU? An atomic mass unit. Have we talked about it?
We read about it.
You read about it. Have we talked about it? No. Biggest reason why? It's pretty useless. Okay? It has very narrow use, particularly as far as the class goes, so I tend to kind of ignore it. Really what it is an arbitrary way to measure mass, like pounds, like grams, okay, like kilograms. It's just a new mass unit. If you're given AMUs, what unit should you use? AMUs. Don't change it, you're fine. Okay?
You're saying the sociocultural context determines which unit.
Yeah. Yep, I'm saying that, but with less fancy words.
Yeah, I don't know what he said.
Because I'm not in that genre. So gallium has 2 isotopes. Right? One of them is 68.926 AMUs. The other one is with 60.11% abundance, and gallium-71. What is the mass of gallium-71 in AMUs to 4 significant digits? Okay. Bring it in the concept of significant digits. Just give me 4 numbers, and we're okay. So how could we go through and solve this?
How much time do we have to do it?
2 minutes.
Okay.
That was actually a question to me asking you to tell me what to write, not you do.
Oh.
If you want, you guys want to do it? No. Okay.
So we have the mass, of the atomic mass unit. So we want to take all the information we have, and then
Take all the information we have and do what with it? Not a bad idea that we could write it down. Okay. We had gallium-69.
What was he trying to say with when it used the word abundance?
What mass? That's our percent, the amount. For gallium-69, what do I know?
You know that there's
68.926.
68.926 weird AMUs. And what else do I know? 60.11% abundance. I also have gallium-71. What information do I have about it?
You have the same percent.
Okay. So I'm hearing a suggestion that I have a 60.11% of gallium-71. What am I trying to find?
The mass of the gallium-71.
I'm trying to find the mass of the gallium-71, right? That's my solve, right? I need that. Okay. I heard a suggestion that I know the percent of gallium-71 is 60.11. Gallium has 2 isotopes. Okay. So if I take the percent of isotope number 1 and add that to the percent of isotope 2, what should my percent be?
100.
Should be 100%. If I take 60.11 plus 60.11, what do I get?
120.
120% of all gallium. So it's not right. Oh, what are you doing? Why are you saying 40?
Oh, because I'm minusing 100%.
Okay. We know the percent of gallium-71 kind of by inference from the calculation or from the question. We know that if I take the percent of our gallium-71 plus, that's a 71, plus the percent of our gallium-69, that must equal 100%. Because I know the percent of gallium, I can now go through and solve. Okay. And we get 39.889%. Okay. Ballpark 40, not bad. Okay, cool. Now what do I do? And I would argue at that point, you've actually started doing calculations without summarizing all the information you've got. What's that? No. Let's not cross multiply. There's nothing to cross multiply here.
Okay, so now we just have to find some kind of relationship between the percent and its mass?
Yes. Say, was there a slide a little while ago where we're like, oh, this is how we determine the weights given to us on the periodic table? Yeah, where we take, say, I don't know, the percent of A times the amount of A plus the percent of B times the property of B, so on and so forth, and that would give us a weighted average. Where's the weighted average given to us? In the question. Shenton, I love where you're looking. Where were you looking? What was that?
Periodic table.
You're looking at the periodic table. Why?
Because it has the atomic number and atomic mass, or
And
atomic weight.
what is the atomic weight? It's the weighted average for that isotope. Because you are given the periodic table, we know that for gallium, where did it go? This is 69.72 AMUs. Do I know the percent of A? Well, I don't know. What's A?
Oh, it's gallium-69. So
Gallium-69, okay. Gallium-69 is A. Do I know its percent?
60.11.
Right? Because it's a percent, there's two ways we could enter it. We can either enter 60.11 per 100 for our percent, or we could enter it in as 0.611. Either way works. It's up to you on how you want to do that calculation. Do we know the value for A? We know its mass was 68.926 AMUs. Do we know the percent for B? What was B? That was our gallium-71. We know that was our 39.89, also known as 0.3989. What was the mass for B? Ooh, say that again. What was the mass for B? B. Why? I don't know it. That's what I'm solving for. I've put in a variable now that can allow me to set this up. Now what do? Solve for B. Okay? However you want to crunch that into your calculator, you can go through and crunch it in, and you should end up with an answer. That answer, for the sake of different colors, let's go ahead and use orange, was... This is when you were supposed to tell me the answer. 71.09? Okay, there's our 4 sig figs. Did everybody get 71.09? I did not calculate that, so you are trusting Gloria with her calculator skills. Okay. As far as approximations go, that's probably reasonable. Why might we say that's probably reasonable? Gallium-69 has a mass that is roughly 69. What do you think the mass of gallium-71 is going to be? Probably similar to 71. Right? So in the grand scheme of ballpark calculations, that's not too far off. And we have an answer. Let's say you punched into the calculator and you got not that, but you came out with the now wrong answer, but it's getting written up there. 72.63. You've written all of this in your show your work. This is a good show your work question, by the way. You've written all this as your show your work. Okay? You'll probably even have a list of multiple choice answers, so you can actually highlight your answer choice. 72.63 is one of those answer choices. You circle that. Did you get the question right? No. Dead wrong. Is your work right? Yes. Guess what you're going to get credit for? All the work that you went through and put into that. Most of the show your work are either 4 to 5 points. The answer is usually only worth 1 of those points, which means all of that work being valid says you get 4 out of 5 points. That's how I grade. Show your work. Multiple choice, you're wrong, sorry, and you lose it all. But that's also why I try to shift the show your work into show your work type formats. Okay? Make sense? Okay. Oh, yeah, we got another quiz, which maybe we'll do next time we meet. Let's take a look at the periodic table. So we're going to jump from Chapter 4 into Chapter 5, because I think this segue makes a little more sense. Anybody tell me what they see up there? Those are weird-looking, different periodic tables. Okay? Why did we not use those and instead use the one on the walls?
Hard to comprehend with those ones.
Okay.
In my opinion, like, they just look.
They're highlighting different bits of information. Okay? For me personally, I would say the upper left is the only one that actually stands out as something useful. Okay? The other ones, I'm not even sure why they formatted them that way, other than they just wanted to be difficult. Okay? But the upper left actually has some sense behind it.
It looks like somebody was tripping on acid when they drew that. Like, what?
Somebody's tripping. Yeah, that's possible. What's that?
It's about how common the element is.
It's how common the element is, probably on Earth, but I'm not positive about that one. Right? So someone went through and just did a shape map for each of those. The bigger the element size, the more of that element is found on Earth. So by looking at that periodic table, I could say hydrogen, carbon, and oxygen are the most abundant elements on this planet. But if I look at our periodic table on the wall, I don't have access to that information. So depending on what we want to pull from our periodic tables or from our organization, we can change the format. We can change how it's presented. Okay? Nobody likes the little circular one? I mean, I would argue the circular one is pretty darn close to what we have.
You explain the format to me and how to read it properly, then I'm sure it'd be fine.
I don't mind it.
Like, I don't mind the way it looks at all, actually, but.
I mean, it looks pretty, and believe it or not, it's got the same organization. Take a look at that B. Maybe kind of hard to see there. Just look in that middle. What is that letter?
Do you have, like,
B. What's directly after it?
AI,
AL,
L,
GA, IN. I can't see that last one, but I'm going to guess it is TL. Where's B on our periodic table? What's underneath B? AL, underneath AL, GA.
So it's like grouped correctly.
It's grouped correctly. Why did they change the format? They decided that they get a better, or maybe even just a more aesthetic way of looking at it.
Which we'll discuss when we talk about rhetorical purposes and visual design.
So we're running, I get maybe 30 seconds, but I'm not a big fan of all this stuff, and you guys can look at it later anyway. Classification of the elements, historically. Remember, we're looking old school historic, 1829, Dobreiner. Okay, don't stress about the name of this guy, but he went through and classified the elements into groups of 3. We take a look, do we have groups of 3? So a group would be a vertical axis. Do you see any groups of 3? No. Why was he doing groups of 3? That's all the elements he had access to. So we saw groups of 3. Okay? And within that triad, he saw very similar chemical properties. Why might they have been calling out, ooh, look at this triad? Also known as maybe a trinity.
Why would they be calling it out?
Yeah, why would he be going, oh, look at, there's a triad.
With some kind of relevance to them?
No religion. Was it the Father, the Son, the Holy Ghost?
Trinity though?
Why are they calling out triads? Because it matches the sets of 3 from religion. Right? When we go all the way back, that's where a lot of this comes from. You look at the next one, Newlands, organize it into sets of 7, right? Known as the law of octaves. Musicians in the classroom, what is an octave? 1, 2, 3, 4, 5, 6, 7, 1, and it repeats. Okay? He saw the sets in music back to our periodic table.
Wasn't this them just applying?
They're applying with whatever knowledge they have.
Right.
If you want to talk about coincidences, we can get into that. Where we'll pick up on Tuesday is looking at Mendeleev's periodic table. Thanks for sort of.